Hi, welcome to Algebra 2 Common Core. In today's lesson, we're going to take a look at a whole new group of numbers that we haven't been introduced to before. These are called the imaginary numbers. So our first question is, what does this I symbol stand for? Let's review by going back to radicals that we know how to simplify. If we see something like the square root of 100, we know that that answer is just equal to 10 because 100 is the perfect square of 10. 3 radical 16, because 16 is also a perfect square, I can take the square root and say 3 times 4, which gives me 12. Now 50 is not a perfect square, so of course we have to break this down into the product of a number that is a perfect square times whatever is left over. So 25 times 2, because 25 is a perfect square, we simplified this as 5 radical 2. We can do the same thing with 72. 72 is the product of 36 times 2. 36 is a perfect square. The square root is 6. So I have 5 times 6 times the square root of 2, which gives me the answer 30 radical 2. And when we take a look at the square root of 0, that's one that we don't look at very often, but 0 is also considered to be a perfect square. The square root of 0 is just 0 because 0 squared is equal to 0. Now notice that none of the examples that we've tried so far have had a negative underneath the square root sign. But in our next example, the square root of negative 4, we're looking for two numbers that are exactly the same, that when I multiply them together, I get negative 4. So far in the real number system that we are used to using, there's no two numbers, no one number that when I multiply it by itself, I get the answer of negative 4. So what we're going to have to do is define a new unit called the imaginary unit. The imaginary unit is going to allow us to simplify square roots of negative numbers. So first of all, the definition of I is really just equal to the square root of negative 1. So every time I see a square root that has a negative under it, I know that I'm going to be using this imaginary unit I. Anytime I is in a number, that tells me the number is called imaginary. Let's try a few examples with this I idea. So the square root of negative 9, I would rewrite that as the square root of 9 times the square root of negative 1. Because 9 is a perfect square, I can say the square root of 9 is 3. But the square root of negative 1 is I. So the square root of negative 9 would be simplified as 3 times I. So there's an example of an imaginary number answer. The same thing happens with the square root of negative 100. We would simplify this as 100 times the square root of negative 1. Square root of 100 is 10. Square root of negative 1 is I. So the square root of negative 100, we're going to get used to seeing that as 10I, another imaginary answer. Now this works pretty much the same when I've got a number that's not a perfect square. This time I'm going to write the square root of negative 32 as the square root of 16 times the square root of 2 times the square root of negative 1. The square root of 16 is 4. The square root of 2 is just radical 2 because that's not a perfect square. But the square root of negative 1 is I. So this answer would be 4 radical 2 times I. Still an imaginary answer. When I try the square root of negative 18, we're going to have the square root of 9 times the square root of 2 times the square root of negative 1. That gives me 3 radical 2 times I for my answer. Now in this lesson, it's going to be important for us to learn about how this I works as far as mathematical operations. So the first operation that we're going to look at is powers of I. When I have I to the 0 power, just like any other number raised to the 0 power, I to the 0 is equal to 1. I to the first power is just itself, so that's going to be I. I to the second power means that I'm really multiplying the square root of negative 1 times the square root of negative 1. Now, don't be tempted to multiply those negative 1's together. Instead, we think about this as when I multiply two radicals together and the radicals have the same radicand, the answer is just that radicand. So I squared is actually equal to negative 1. When I get to I to the third power, I'm going to say, oh, well, that's just the same as I to the first times I to the second. I to the second, we just learned on the previous box, is equal to negative 1. So I times negative 1 is just equal to negative I. So far we see that we have answers of 1, I, negative 1, and negative I. Let's go on to I to the fourth power. For I to the fourth power, well, there's several ways that I can do that. I can either say I to the first times I to the third, or I can write it as I to the second times I to the second. Either one is going to give me exactly the same answer, and you might want to pause the video and try it either way and see what answer you get. I to the second is just negative 1, so I'll have negative 1 times negative 1, and I see that that answer turns out to be positive 1. And again, try it out with I times I to the third and see if you get the same exact answer. For I to the fifth, another way of writing that, and again, there's multiple ways to do this, but one way of doing it would be I to the fourth times I to the first. We know that when we're multiplying and the bases match, all we need to do is add the exponents. Well, we know from the previous box that I to the fourth is equal to 1, so 1 times I to the first is an answer of I. For I to the sixth, again, several different ways that I can do this. One nice way would be to do I to the fourth times I to the second. So I to the fourth is 1. I to the second from above is negative 1. 1 times negative 1 gives me an answer of negative 1. For I to the seventh, how about if I say I to the sixth times I to the first? I to the sixth is negative 1 times I gives me an answer of negative I. Now I'd like you to pause the video and try the next 4 examples. And again, remember there's multiple ways to do all of them. Come back and we'll talk about what answers you got. Looking at these powers of I, I've got that I to the eighth turned out to be 1. I did it by doing I to the sixth times I to the second, but you could have done I to the fourth times I to the fourth. There's many different ways of getting I to the eighth power, as long as your exponents add to 8. For I to the ninth, that turned out to be I. I to the 10th is negative 1, and I to the 11th is negative I. So if we take a look at this, hopefully you're recognizing that there's a pattern. These answers keep repeating. If you look closely, you see that there are actually 4 possible answers. 1, I, negative 1, and negative I. So the pattern is that the answers repeat in the pattern of 1, I, negative 1, and negative I. Now, sometimes it's nice and easy to show this on what we call an I wheel. So make sure you take the time to draw the I wheel in your notes on the right spot in your note packet. So I'm going to draw this as first a set of axes with a circle. A wheel is a round circle that just keeps going around and around. On the right side, I'm going to start with I to the 0 power. And I know that I to the 0 power is equal to 1. Then I go this direction and say I to the first is equal to I to the second is equal to negative 1, I to the third is equal to negative I. If I come back to I to the fourth, it's the same answer as I to the 0. And so on around the circle. So I to the fifth would be this answer right here. I to the sixth, I to the seventh, I to the eighth, I to the ninth, I to the 10th, I to the 11th, I to the 12th, and I could keep going for as many exponents as I needed to. Now, what I want you to think about as we work through the next few examples is there a way that we can use this pattern to make our calculation easier? We can, of course, always go by this circle as long as we learn what this circle is. You'll notice that I set up the circle so that I've got the real numbers, the 1 to the right of the origin and negative 1 to the left of the origin. So on the horizontal axis, we've got those real answers. But on the vertical axis, we've got imaginary answers. Positive up here, negative down here. So it should make it nice and easy to remember your I wheel. So in exercise number 2, we want to simplify each of these powers of I. Again, there are multiple ways of doing it. We can use our wheel. If you see another shortcut way to do it, I want you to try to do that, and we'll talk some more in class about what that shortcut way might be. I to the 13th should be the same answer as I to the first. If I go around my wheel, that's what's going to happen. So I to the first is just equal to I. I to the 20th should be the same answer as I to the 0. Let's think about that for a minute. What do 20 and 0 have in common? That gives me an answer of 1. I to the 62. Wow, would I have to count that out 62 times? Or could I notice that I to the 62 is the same as I to the second? Think about how I'm going to figure out what it's the same as. And that's going to give me a negative 1. I to the 35th, that's actually the same as I to the third, and I to the third is negative I. Now I'd like you to pause the video and try the U-try-its and come back and check your answers with mine. Check your answers with mine, and again, I want you to think about how we can make our work easier to figure out what entry on the I wheel each one is congruent to. Again, we'll talk about this in class tomorrow. We need to define a set of new numbers. In standard form, these numbers are A plus BI. Now, what we really have here is that A plus BI is called a complex number. A complex number actually has two parts. The A part, the part without the I, is the real part of the number. The BI part is the imaginary part of the number. So up until now, we have been dealing with all numbers that are real. What that meant was that they had an imaginary part that was just 0. Really, all numbers are actually complex. So a real number could be written as this, 3 plus 0i. A purely imaginary number could be written like this, 0 plus 2i. But when I've got both a real part and an imaginary part that are not 0, I have a complex number, and that complex number would be something to the effect of 5 plus 4i. Now, it's not necessary that I have plus between the pieces. I could have minus. Either part could be a negative part. I can also have fractions and decimals as the real part or the imaginary part. So in the next few examples, we're going to take a look at writing answers in this standard form. Notice that we always put the real part first and then the imaginary part. So for number 3a, I've got 4i to the 27th. I've got to simplify each part of this. I cannot, and I repeat, I cannot add these pieces together. These are not like terms. So if they are not like terms because they don't have the same exponent on the I need to simplify each one first. So 4i to the 27th. I to the 27th would be equivalent to I to the 3rd. And we know that I to the 3rd is equal to negative I. So I've got 4 times negative I, which is negative 4I. 8i to the 18th. I to the 18th would be equivalent to I to the 2nd. I to the 2nd is negative 1. So I've really got 8 times negative 1. 8 times negative 1, of course, is negative 8. Now, this is not normally the standard way that we leave our answer. We want to put the real part first, negative 8, followed by the imaginary part, negative 4i. So in simplified form, this answer would be negative 8 minus 4i. Let's try the next one. I to the 90th, that's going to be equivalent to I to the 2nd. I to the 2nd is negative 1, so I've got negative 2 times negative 1, which is positive 2. I to the 64th is actually equivalent to I to the 0. I to the 0 is equal to 1, so I've got 15 times 1. So this time I've got 2 plus 15, which gives me a final answer of 17. So you'll notice that this one is a real answer with no imaginary part. Take a look at the original exponents and see if you can think about why we ended up with only a real part and not an imaginary part. Compare this with example A, where we did get an imaginary part. We'll discuss in class tomorrow when we're going to get an imaginary part and when a real part. Now, moving on to example C, I want to simplify each part. So I to the 37th, that's equal to I to the 1st. So this is going to be 10 times I. I to the 46th, that's going to be equal to I to the 2nd, which is negative 1. So I'm going to have negative 4 times negative 1. I to the 55, that's equal to I to the 3rd. I to the 3rd is negative I, so I'm going to have 6 times negative I. So this answer is 10I plus 4 minus 6I. I'm going to start with my real part 4, and then I can add together those imaginary pieces and say 10I minus 6I is plus 4I. So this again is a complex answer with a real part and an imaginary part. Let's take a look at this picture of the complex number system. We used to live in this world over here. This was the real number system. The real numbers were divided up into the rationals. Rationals were any numbers that could be written as a fraction or as a decimal that either repeated or terminated. The integers are examples of rationals. Whole numbers are rationals, and natural numbers are rationals. Notice that the integers have both positive and negative whole numbers, including 0. The whole numbers do include the zeros and then all the positive integers. The natural numbers are almost the same as the whole numbers, except that the naturals don't include 0. So as we progress from outside to inside, we see that our system is getting smaller and smaller. Technically, it's not getting smaller and smaller because we can't really count all of the numbers in any of these systems. Now, the opposite of rational was our irrationals. They cannot be written as a fraction we have two very important examples of irrationals, pi and e. Those are decimals that do not come to an end. They don't repeat and they don't terminate. Now, here we have our new kind of number, imaginary numbers. Imaginary numbers are the parts that have the eyes. When we put the reals together with the imaginaries, we have a real part and an imaginary part that makes a complex number. Now I'd like you to pause the video, write down the following you try it examples, simplify in standard form, and then come back and check your answers with mine. Check your you try it answers with mine. So in number 1, I got the complex number -7 plus 3i. Check your conversions. So I to the 26th was equal to -1. I to the 37th was equal to I. For number 2, I got the final imaginary number 6i. Both I to the 17th and I to the 29th are equal to I. So when I simplified, I could put together those like terms to get 6i. And for number 3, my final answer was the complex number 6 minus 14i. Again, look at all three parts. You have to simplify each one first. They cannot be added together. A common mistake with these powers of i's is to try to combine terms that don't have the same I. But I can't do that because I don't have like terms. I've got to simplify first and then combine. We'll be doing a lot more work in class with rewriting both complex and imaginary numbers tomorrow. Have a great night, and we'll see you next time.